Okay, good morning, everyone. My name is Chirag. I'm the consultant here at Sigma-HSE. Today, I'd like to give a webinar on how to achieve DSEAR and ATEX compliance without replacing old equipment. We'll just wait a few seconds as the attendees pile up or enter the chat, enter the webinar. Just a minute. Okay, yes. So good morning, everyone. So today I'd like to give a presentation webinar on non-electrical equipment risk assessments. It is a way to achieve compliance for pre-ATEX legacy equipment. Here is the overview of today. So we'll have a very brief introduction to DSEAR and ATEX, especially regarding equipment, ignition sources, flammable atmospheres, the risk assessment side. We'll then talk about using the standard, which outlines the methodology for risk assessing an equipment and to certify it safe for the hazardous area it's in, which typically involves the assessment procedure. So what are the steps you typically do, like visiting the site, visiting the equipment, attaining all documentations, inspecting it as such. Also included in this webinar, we'll go over a worked example, which would be a mixer unit to go through. So before beginning the webinar, we'd like to introduce ourselves, Sigma-HSE. So we have a presence in the UK, India, Asia Pacific, and now the USA. We primarily focus on process safety consultancy, laboratory, and as well as training among a wide range of process safety needs for your factory. Our expertise, as I mentioned, is broad in the spectrum of process safety, which is, yes, the consultancy, engineering side, the testing, the training, and basically to achieve compliance with your local safety regulatory. With the consultancy side, we typically offer, well, basically hazard identification, identifying your hazards from a basic point. So it can be DSEAR assessments, ATEX assessments, both desktop to actual site verifications to hazard operability. So your process hazards, how you operate a certain part of your site. As well as we also do the training workshop. We looked into functional safety, chemical reaction hazards, which is also a very interesting field, which we have numerous webinars on. Another aspect we have is laboratory testing. So typically flammability data, onset temperatures for, say, your chemical reaction hazards, as well as a wide range of testing. Some of the values in this testing is actually needed for undertaking your risk assessments, as we'll talk on later on. Okay, so the first step, I'd like to go over an overview of ATEX assessments in general. So this should be just very brief, and where there's non-electrical ignition equipment risk assessments come into it, and how to reuse existing equipment, how to reuse it so that it is certified safe. So yeah, so typically in an ATEX assessment, there's three main processes or three steps I'd like to say. First is to determine where flammable atmospheres occur, which gives you the hazardous area, so the physical zone, the bubble where flammable atmospheres are created. So this can be something that's being tipped, poured, that will create flammable dust clouds, or something that can release vapors, say if it's within the headspace of a vessel, or if you're venting something, or typically when something leaks, that creates a flammable atmosphere, which is the hazardous area. The next step is to identify, say, ignition sources, or in this webinar, we'll be talking about equipment being as an ignition source. But ignition sources can typically be, although there's 13 types, typically something is, there is hot surface, something can get hot. There is mechanical sparking, so there could be some friction, there could be some collision impact, creating some heat and energy. There can be unsuitable electricals. For example, flammable atmospheres can ingress inside your electrical, like a junction box, an isolator. So it should have its typical protections. And very big one we talk about is static electricity. So something can release as a spark if there's a difference in charge. So yeah, that would be your ignition source. That would be step 2. And step 3 is to identify equipment that are not suitably protected. So you could typically get it ATEX certified by new equipment, which typically costs 3 times more than a normal price of equipment. Also consider that there's lead times when you're purchasing new ATEX rated equipment. And there is a big or. You could either undertake a risk assessment depending if they're legacy equipment. So before ATEX came into fruition, into legislation, which is in July 2003, you can actually take a risk assessment to certify the equipment safe. So this is the function of this webinar, which I'll talk more in the next slides. So yes, equipment risk assessments. So we follow the standard is ISO 8079-36. It outlines a methodology, a process, and a typical risk assessment table. So what manufacturer uses, or if in this case we could self-certify using this methodology to risk assess an equipment, find out the weaknesses. So that if there is an ignition source, what are the scenarios, what safeguards you have, and if there's any gaps in this, you may have some recommendations coming out from this typical this risk assessment. And the purpose of this methodology is to assign an equipment protection level, which again is the category, which again is the zone. So categories come in 1, 2, and 3. So, and that's linked to the zone. Say category 1 is zone 0, zone 20, so a flammable atmosphere that is present continuously. Category 2 is zone 1 and 21, depending if it's gas and vapor, like flammable atmospheres that come briefly, but is part of normal operation, say during startup shutdown. And then there's category 3, which is zone 2 and 22. This is through abnormal operation that you can create flammable atmospheres. Say, for example, something leaks or something rips, like a filter inside a dust collector, and say powders can carry over and create flammable dust clouds, albeit for a short period of time. So you could, using this methodology in this standard, with this methodology you can certify your equipment as safe and classify the equipment as a type H. So this standard, or this methodology, is predominantly used by designers of new equipment, say the manufacturers, but it can also be used as a basis to assess legacy equipment. And depending on the category, which is the level of risk, so the category is linked to the zone and how often a flammable atmosphere occurs. So if it's if the zone is more onerous, like a zone 0 or 20, that affects whether you can self-certify your equipment. So typically, post 2003, if it's category 1, which is a 0 and 20, it is not recommended to undertake use this methodology. This is due to the fact that the manufacturer of the equipment usually has access to the intimate knowledge behind an equipment. Say they'll probably know, for example, like how the shaft is created, what is the material of construction, and that's why it's always good practice that post 2003 is to usually buy ATEX equipment. So for your site, you may have legacy equipment, and you can use this risk assessment methodology to certify it safe. Let's go on to the next slides. So this standard outlines a methodology, which is basically following 3 steps. So you outline the ignition source. So what type is it? Is it hot surface? Is it static electricity? And mechanical sparking? Those are the 3 major ones that we can assess. And of course, because it's non-electrical, we can't assess unsuitable electricals. That requires a separate assessment, or there's a separate standard and methodology for that. So yes, step 1, identify which type of ignition source you have. And step 2, which is the trickiest part of this assessment, is the scenarios. So each scenario, which I'll talk through in the next slides, has so you outline a scenario. Which is it relevant to your equipment? Say if you're risk assessing a pump or a screw conveyor, and you have to have the right scenario, so you can give a reason if it's present or not. And this is based on experience. And yes, and I will talk about this in the next slides. And then the third step would be, what safeguards do you have? So safeguards could be operational, could be maintenance, it could be something like an instrument, something that measures temperature to prevent hot surface becoming effective, or it can be even through testing. Maybe your equipment is run like at full load for a period of time. So yes, this standard outlines typical safeguards. It also gives examples of testing, say specifically for hot surfaces, maybe the shaft can have a temperature thermocouple on it, and it's been tested that even at highest loads, it never goes above a certain temperature. But again, this is discussed in detail in this standard, which I recommend the viewers have a look at. So yes, so determining the scenarios for each ignition source, it depends on the level, the category assigned on it. So the more onerous, more dangerous flammable atmospheres appear, like a zone 0 or 20, you have to consider what type of malfunctions. So malfunctions can be in normal operation, it can be expected, it can be rare. And of course, the category affects the level of protections you need. So for, say, category 1, a zone 0, you need to consider all scenarios, like expected malfunctions and rare malfunctions. Typically, this is like something malfunctions, like something deforms, like a bearing can deform, it can misshape. That could be expected malfunction, or something rare, like this bearing connected to a shaft and it misaligns and then it snaps off. So that is an example. I guess the next slide I will talk about that. So yeah, understanding which scenarios apply to your equipment. These are just some examples that something can, yes, misalign, some system that fails to monitor or has a lack of lubrication. That could be something expected. And something that's rare, like, let's see, okay, a motor is run for long periods of time and it goes undetected and it reaches a certain ignition temperature. That is a typical example of rare, for example, if tramp metal come into your powder handling system, but in your equipment you may have some safeguards against it, like a metal separator, a magnetic trap. So these are all typical malfunctions and some scenarios to consider. So here's an example of a category 1 equipment. So it's a zone 0, I believe a zone 20 as well. So it mixes a flammable powder as well as liquids going inside it, flammable liquids. Just to show you the level of safeguards they have. So to prevent hot surfaces, there is a monitoring system. So thermocouples on the bearing, testing of maximum temperature under load. So the standard outlines a typical testing scenario to show that, say, the shaft and within the mixer, or let's see, the blades are turning, that it doesn't go above a certain temperature. So these are all safeguards. I would also probably add, missing in the slide, is maybe they have a strong maintenance regime, that they may even have like bearings that are replaced regularly. They replace before the bearing life fails. So I'll be talking about bearings in the coming slides. So for mechanical sparking, they may have vibrational monitoring. So it might monitor if there's any misalignment in the motor, the shaft, that it may have an automated switch off system, like it trips off the system, therefore preventing an ignition source in rare conditions like the shaft snapping off or misaligning, prevent it from occurring. So you have that safeguard. There's For static electricity, there may be limits on insulating surface areas. So this is also another standard. It's the Electrostatic Bible, 6079-32, which has a table for how much insulating materials or surface area you're allowed, based on the gas group. So I wanted to show you that this is a typical example of the safeguards there is. And when you buy this ATEX rated equipment, they will have a risk assessment to show that. And the risk assessment is using the methodology of the standard, which is the 8079-36. So now the assessment process. So typically, after undertaking a DSEAR assessment, you outline your list of electricals and equipments in hazardous areas. You find out which is certified, has the protection, and some equipment that don't have the protection. You generate a group like in a spreadsheet. The second step would be assemble the plant, equipment, and flammability data. So you need to know the ignition temperatures. So what is the allowable surface temperature? So when you do consider hot surface in your risk assessment, what temperatures do they go up to, or what is allowable? Then you may need to consider ignition energies. So if the ignition energy of your worst case powder, or your worst case powder has a very high ignition energy, maybe you don't need to consider static electricity from discharge, so spark discharges. You may not need to consider mechanical sparking because the ignition energy is very, very high. So these are just some useful ideas of what flammability data and how they help in this risk assessment. So yeah, it's a simple process. So you generate your equipment, what needs to be assessed, you have all the relevant data or the worst case data, go look at the equipment, go see it in person. I'll tell you why it is necessary to do that. Identify the inherent ignition sources and the examples behind it, if it can be effective. Conduct the risk assessment, which is generate the table, fill in the table, put in the necessary safeguards. There will always be something that's outstanding. There will always be some gaps in your safeguards. For example, so typically when I do these NIRAs, there's always things missing in the maintenance procedure. Although, say, the maintenance operator, they do undertake it, but they may miss it out and it may not be written, written physically into your procedures. So yeah, typically, for the outcome, you do get some recommendations. You may need to consider new measures, so safety functions. So this could be instrumentation, temperature monitoring, vibrational monitoring. Again, I will talk about this in the preceding slides. So yes, so what are your requirements for your team? So typically someone that is familiar with equipment, which would be the operators, the people actually running the equipment, what type of systems they use. They'll have understanding of the operation. So for example, maybe your equipment is run in batches, so this may allow a degree of cooling. So that can be used as a safeguard against hot surfaces, for example. You may might need the equipment manufacturer sometimes, because they, again, as I mentioned previously, they have access to some knowledge that may not be so evident in, say, the manual or how it's connected. They may have understandings on the logic or its design. So why was a shaft not welded rather than if it's screw fitted or if it's bolted? This, again, provides more information, that provides more reasoning and justification for if safeguards are needed or if there's any remedial action. And yes, of course, so a person with knowledge of the equipment, maintenance history, maintenance procedures, or any previous failures, this really helps during the assessments that I've undertaken. They may be, over time, when you have an equipment especially if it's pre-ATEX, 2003, almost 20 years, modifications have been made. So this is why someone, or a person with this knowledge of the changes has understood why these modifications have been made, and has it affect the integrity of the equipment, especially from an ATEX or atmospheric explosive atmosphere perspective. For example, maybe some spares may not be available now, say, compared to when it was first purchased, and they might say, hypothetical example, they might use a different seal, and that might compromise the continuity to Earth. So this may lead to, say, static discharges. So these all things interesting should all be considered, and this is part of our team requirements. So what are the equipments typically assessed? These are non-electrical equipments, so something that's rotary, typically transferring systems like pumps, conveyors, fans, extraction fans, blenders, mixers, agitators. It can also be, in the next slide, it can also be low-risk equipment, say slow-moving valves that just so happen to be in a hazardous area. It can be pneumatic dampening systems where they may be like an external zone, but you can use this same risk assessment on low-risk equipment. So it doesn't necessarily always have to be the conveyors, the sifters, the sieves, the reactors, or the reacting vessels. You can apply this methodology for equipment, such as the low-risk ones, as well as, say, systems, depending on what they are and what ignition sources are, just as long as they don't have electrical items within them. And if they do, they need a separate risk assessment, and they follow a separate standard. Yeah. So yes, so the first step would be to acquire all the information needed. So that will be typically manuals, it'll be flammability data, understanding the materials of construction, that's quite important. So know what type of seals you have. Is there anything insulating? Is there anything that's going to compromise something that could create ignition source? As we mentioned, the three main ones we assess in this is static electricity, say for example, isolated metal plant. We look at hot surfaces, so something like a type of seal, maybe there's a gap in the seal that allows powders to be trapped inside of it. And that's just an example. We also look at mechanical sparking, so just need to know, say, the rotational speeds of your rotating item. So the shaft inside a screw conveyor, it rotates at a certain speed, and that might affect if the possibility of mechanical sparking being effective. Also good to know the existing mitigation systems like instrumentation, metal detection, say upstream, alignment sensors. I'd go as far as saying maybe you could even consider inadvertent monitoring of your equipment. For example, you have a transfer pump. Maybe you are monitoring in your control system the ampage. So maybe if it's an indirect monitoring system, so if the pump is failing, say if it gets blocked or some sparking is occurring, maybe it can be detected on indirect systems, although that's not necessarily a bad thing, but it's good to capture it in your risk assessment. Like, as I mentioned, you may have like blockage sensors, you may have monitoring the power if it appears on your control screen. Let's see. Again, the drawings, plant data, speed. Yep, that's very important. Expected temperature rises. So again, as I mentioned, the standard does outline the methodology for testing your equipment under load to show and have evidence. So that's the key thing, evidence to show that this specific scenario or this temperature, for example, can never occur, and you have the evidence to back it up. Again, this whole risk assessment, this NIRA, as we say, is about having evidence, having it documented. So in case if an incident does happen, the regulators can inspect or look at all the documents and evidence, and it could be some scenarios can be ruled out, or it aids in such an incident if that occurs. So I apologize, I digress. I'll go into the next slides. So procedural informations, as we mentioned, there's a whole host from operating, maintenance, to even commissioning, I'd say is probably missing on this slide. So how it's installed. Sometimes I've come across when there was a reactor, it was an agitator, and it was the agitator and the motor system was taken off and then it was put back in, but its installation procedure wasn't done by a competent engineer. They didn't use a laser alignment, for example, and because the installation or reinstallation, which I guess is the maintenance procedure, it wasn't installed correctly, and this left a small gap in the seals. So this is things to consider. Also, regarding operating procedure, I'd say also if your process is running continuously, how is it cleaned? Is there any residual, say, for example, powders? Is it cooled? I mean, does this help in understanding that maybe if your equipment is used in short batches, maybe it might allow a degree of cooling. So for example, and a scenario could be heat is being conducted from an external motor through your shaft inside a screw conveyor. But your safeguards could be that the process is run in short batches, so it allows a degree of cooling. Or maybe in your operating procedures, you may have external cooling, like so you have in a pharmaceutical facility, you have air changes that the room is ventilated. Maybe that can help, maybe not help as much, but it helps to put into your safeguards. You can add every small bit of safeguard. It benefits the risk assessment, and it's just more justification. So if anyone ever asks questions, say, and a regulator looks at all your safeguards, and it builds a nice picture, let's put it that way. Maintenance procedures, yes, records. Usually when I undertake NIRAs, there's always gaps in procedures. And for example, operators, they may inspect, they may visually check like a transfer equipment, like a screw conveyor, but they may not have it in writing that actually, wait a minute, you should be checking for trapped powders. You should be checking the conditions of your seals. So they may change the bearing. So what I want to say is that there can always be some things. There's always some gaps in this. And again, this is the reason why this risk assessment is very beneficial. Always good to compare the manufacturer's instructions compared to how it is run currently. Of course, pre-ATEX, maybe manufacturers once so focus on, say, preventing ignition sources like they are now with ATEX rated equipment, but it's just good to compare it, just to see that you're in line with the instructions. Say, for example, which in a manual they may say, oh, you need to replace your bearings at this many hours, which is below the life or the useful life, and just see if there's any inconsistencies. So yeah. Yes, so it's always good to look at the equipment. You could always find signs of damage, you can find rust, you can find even some even some safeguards you may put into your risk assessment may be missing. For example, maybe you might have earthing clamps onto your equipment that at the time you look at it may not be there. So, and that could be because there's some gaps in your procedures. So yes. Also, as we're assessing pre-ATEX equipment, it usually is that they degrade over time, the efficiency degrades, and this may affect the control system, it's opening of a control valve, although it's inherent that things degrade over time, and it's always better to see it, to see the damage. Is there any rust? Usually, typically in my assessment, I've seen many times bolts are not installed properly, so it may not be necessarily a NIRA risk, but it's there to show you that things can be better that way. So here's just a simplified layout of the risk assessment table. In the standard, it's a little bit more, a lot more difficult to read, but this is just simplified and just show you how you fill in the table. So step one, you'll identify the ignition source. Step two would outline the scenario and what type of malfunction does it occur. So doing normal operation, just that the fact that there is, in this case, that the bearing is rotating. Sorry, there's a rotating part and there's a static part to some rotating equipment, say at the seal, and this can develop temperature. That you have surface temperature. That's part of normal operation. And yes, then you have the typical safeguards in place. So this is putting it into a simplified table. So you have weekly lubrication, you have inspection, you also have the speed of the equipment. So if it's below a certain speed, this may prevent against mechanical sparking as well as hot surface. So if it's slow speed, it's not the moving part and the static part is not likely to generate temperature. And you'll have a recommendation. So you could do testing on this, say over a period of time, which as the standard outlines gives a better indication. Again, further evidence to show that this scenario and this ignition source has a suitable safeguard. Yeah. So just some more examples of types of scenarios to consider. So here we have a belt-driven conveyor. Something can fail, so the slips of the belt can fail. The seals can wear. There could be a loss of lubrication or over lubrication if there's any consequence to that. I could also add if this equipment had a flammable vapor atmosphere, maybe the belt drives need to be anti-static to prevent, say, static discharges. So these are all things to consider when undertaking your risk assessment. So yes, ignition control by hot surfaces. Is it below the allowable temperature? So this should be based on flammability data, like auto ignition temperature of a vapor, or in the case of dust, it'll be based on a safe margin between the minimum ignition temperature and the layer ignition temperature. Do you have monitoring systems in place, like a thermocouple? Does it have an automated action? Yes, so some bearings that I've seen in some factories, they do have purging. So I think it's called hanger bearings, where they purge a little bit of cooling air just to stop the trap powders coming into the seals. So between like long pieces of equipment, so typically in conveyors, this actually acts as a safeguard. So you're cooling your system. So if you consider in your risk assessment, you have hot surface, you have this scenario, but this can act as a safeguard. So yeah, this is good. I'll probably add in, you could even put in temperature stickers. So for really cheap, you can get these stickers that change color depending above a certain temperature. So when an operator goes around for the walkthrough, they can detect it, and this can be used as a safeguard against certain scenarios pertaining to hot surfaces. At sites, they typically have thermal imaging. You can have regular thermography. So if someone goes around the site and take temperature monitoring of external equipment, and this can be used as a safeguard. So for mechanical sparking, you can typically have a range of safeguards. So typically they can be vibrational monitoring, could be just general inspection, looking for rust. It could be procedures, so making sure that your whatever that's rotating, that it is suitably attached onto it. So if you have, like, for example, a blender mixer that has a is it welded, is it screwed on, and if it is screwed, does it have a certain torque to it, just to make sure it has to reach this force that is suitably attached on. There's also other equipment as instrumentation you could use, such as vibrational monitoring. So if something misaligns, again, as we mentioned, it could have an automated shutoff. So this may be a suitable safeguard against mechanical sparking, which is, say, something misaligning. The key is to detect it before it becomes effective, which is the purpose of safeguards. So plant tours, so walkthroughs, that can be even just part of your maintenance procedure. Just check the integrity, that it is running, there's no noise coming out of it, out of your respective, say, rotary equipment, for example. I also mentioned there's belt slip detection. So anything that you could be used for predicting something that's gone wrong, like say something is blocked or something has misaligned, you could use, as I mentioned, indirect methods of detection is your safeguard. So one thing to note interesting part about bearings is they follow a bathtub curve. So usually, and in manuals, they do recommend to replace it at the end of its useful life, because after that it wears out and it goes in an exponential, so it fails very quickly. So sounds familiar with other typical bathtub curves. Well, for static electricity, so things to consider: your equipment should be grounded, have continuity to earth. Consider it during time, because it's a legacy equipment, so you've had the equipment for such a long time. It maybe some modifications have been made, maybe alternative spares are used that's not approved by the original purpose. Consider also the individual components within, say, a rotary equipment, like the seals, the bearings, anything that could be insulating and then isolating could be a risk of, say, static electricity being formed. Consider propagating brush discharges. Yes, so I've been on a site that had a long belt conveyor. It was conveying sugar. They replaced the belt on it, but with a non-ATEX, ATEX marked belt, and it did have some layers on it that, although maybe wasn't an issue, but it's always best to follow your manufacturer's manual, or to ensure that controls are in place, that you have spares in place for, say, equipment items, components, and this should be captured in the risk assessment, that it is a safeguard that if your equipment ever becomes isolated and creates a potential static electricity ignition source, you have the safeguard, which is, yes, spares in place, earthing continuity checks. So anytime you take apart an equipment, say an extraction fan or a dust collector, that when you put it back, you do the testing, and it's been documented, as mentioned previously about the paperwork. And yes, so documentation. So NIRA is something that's continuous. It's a document that is updated. There's usually actions that come out of it. There can be templates that you follow these structures. There's a typical, like a structure, you can make these risk assessments, and they have actions out of it, just to get, maybe sometimes you may change your equipment purpose changes. So now you may have different materials into being used, so you may need to get different surface temperatures, allowable temperatures allowed within your equipment. And if that temperature has been reduced, then maybe you may have to do testing again to show that this equipment never goes above this temperature if it's affected by it. So this, as I mentioned, is a life document, typically reviewed every 2 to 3 years, akin to a like a DSEAR assessment. And things can change. As I said, sometimes equipment that was used in batches, and maybe you may have used that as a safeguard against, say, an ignition source like hot surfaces, maybe it could be repurposed in the future. So you have to undertake your NIRA again. If it's reused in the future as in a continuous process, then you have to recheck all your, say, temperature loads, if it's possible for ignition, some ignition sources to become effective. So yes, now we'll go through a example of a mixer. Here we go. So as I mentioned, the first step is we have this table generated from the standard, which outlines the type of ignition source, the scenarios, the safeguards, any weaknesses and improvements, which is the recommendations essentially. A table would look like something like this. So you outline every ignition source as per the standard. So there's 13 types, and then you say, is it effective? Yes, no. And if it's not, you justify why it's not there. So for example, maybe your ignition energy, your MIE, is very, very high. So you can probably rule out, say, spark discharges in static electricity. This is just some examples. So they can be, for mechanical sparking, they'd be trapped metal, something like bearing malfunctions, misaligns or deforms. So this is what typically you'd fill in. But of course, the three main ones that I usually look at is, hot surface, mechanical sparking, and static electricity. So here's a scenario. It's a open barrel mixer that handles flammable liquids, producing vapors. and flammable powders. So the zone has been assigned. So internally there'll be zone 1 and 21. And there can also be, say, a spill or vapors lingering around in the area. So there'll be an external zone 2, 22. So here's the situations you consider. Because it's a category 1, zone 1, you have to look at normal malfunctions as well as expected malfunctions, which is something that is misaligned, but not to the rare malfunctions, like something that can misalign, but not snap off, or some welded parts falling apart, for example. So some examples could be of hot surfaces. So that'd be the first ignition source I would look at. Some scenarios would be the shaft could be heated by the upstream motor. So the motor can get hot, and that drive system can heat the shaft, heat the bearing, then the shaft. There could be heating of product mixture. Maybe there's an ignition source like exothermic runaway, which again also another ignition source to consider. But with exothermic runaways, you usually have your own. Usually have other process controls, another risk assessment on that, which be typically from, say, a hazard operability study. There could be a lack of lubrication for, I guess, the drive system. The bearings could deform, so that could lead to misalignment, and maybe the blades can attack the walls of that valve. That makes sense. So for mechanical sparking, yes, there can be trapped metal, like rust, something that inadvertently could be left in the bulb, albeit maybe the bulb is a little bit small, so it should be detected if it's an operator. Again, an example of a safeguard. Yeah, bearing can misalign, deform, and then misalign, leading to the shaft falling out. There could be speed control fails. Maybe the speed of the agitator will run a lot faster than usual. It may lead to sparking, only if this agitator was a slow speed, maybe. So even if it did misalign and hit the wall, it wouldn't be an issue. But maybe your control fails and the speed of the agitator goes fast, like above 1 meter per second, then yeah, the risk is increased. But this is just an example. So static electricity, as you can see, it can be isolated. The whole body is kind of isolated by having that wooden pallet, as you can see. Maybe the powders or the things going, so the material going into the equipment can be isolated or fed from unearthed bodies. That's something to consider. It may be an issue on the lubricating oil. Say, maybe there's a conductivity and it can create discharges in a vapor-filled atmosphere. So around this mixer, say if there may be a zone 2 bubble, say zone 2 around it, maybe that could be an issue. Again, insulating parts within the bowl. Again, from the photo, it doesn't appear to be, but you just never know what. Again, highlights the importance of going on site, seeing the equipment, and just taking notes of where anything that's insulating or something that could compromise and create effective ignition sources. So yes, so your typical safeguards, yeah, it could be instrumentation, could be procedural, and usually it is procedural and operating procedures. So that, as I mentioned, it could be run in batches. Maybe there's a purging process, maybe there's a cleaning process that cools down your bowl, or maybe you have an operator standing by and is inspecting it, and this adds as a safeguard. So that is manually supervised with a manual shut-off system, so to prevent an ignition source becoming effective. And as I mentioned, there will always be gaps. There will always be something that's probably not usually written, but usually in ATEX rated equipment, this has all been considered. So if you're the manufacturer, you're doing this risk assessment, you would find out, and there'll be recommendations out of it. So you put that into your manual. But in this case, whereas when we're trying to recertify, so certify existing equipment, you put that into your procedures. Yeah. And so the assessment table in the standard looks something like this, but it's very similar to the simplified simplified risk assessment table I showed in the previous slides. So ignition source, so you have that type static electricity, then the description of the scenario, how it, and then you put it into, if it's a normal, what type of failure it is, then you have the reason. So why is it, can it become effective? So for example, just running it in normal operation, this can be expected. So just having a bit of a justification text. And then you have the descriptions of the measures applied. So you have operating procedures, you have it's maybe a material construction, among the many levels of safeguards I've talked about previously. So then you reduce it. So you reduce the risk from a normal malfunction, normal malfunction, and then you move it across the spectrum to make it a rare. Then this gives you a resulting equipment protection level. So you undertake this assessment for, and you consider all the scenarios for, say, your ignition source types. You come out with safeguards, there will be recommendations coming out of it, and you can, resulting would be the lowest equipment protection level, the lowest EPL. So for example, if this system, you need a minimum EPL of DB or GB, which is category 2, zone 21, zone 1, you have to make sure that all your safeguards move along. So it moves along once the safeguards have been applied to your scenario. I think this is very similar to other process safety analysis tools like a HAZOP, like a SIL, LOPA. You have the scenario, then you put in the safeguards in place, and then then you evaluate the risk behind it. So it starts off high risk with the safeguards in, then it becomes a lower risk. So it's a similar type of methodology. And of course, the standard, I really recommend the viewers of this webinar really have a read of it. It's very interesting. It's got lots of fascinating topics, especially regarding non-electrical equipment, how they operate. So yes, to summarize this webinar, we've gone through a background, what is ATEX equipment, ATEX protected equipment, what assessment procedures that manufacturers or users of the equipment can use, how to prepare for it, what ignition sources they are. And I guess the tricky part of this such assessment is the example scenarios, understanding the scenarios. Is it actual credible? Maybe it's not credible. And having a full range spectrum of the safeguards in place. So safeguards can be a range of systems. So it could start at procedure level, process control, instrumentation, and there's always be gaps and places for improvement. And that's why this NIRA is, although risk assessment is a continuous risk assessment that may give out recommendations that need to be implemented over the use and life of the equipment. Yes. And yes, that's it from myself. If you have any questions regarding this subject matter, if you like any advice, impartial advice, then feel free to contact us at Sigma-HSE.com or email me via info@Sigma, or my email is CSHETH@Sigma-HSE.com. And I really appreciate everyone that's here, and I hope it's been of benefit to the viewers and listeners of this webinar. I'm happy to help out if you can find a way to contact me. Again, this Sigma-HSE do undertake NIRAs. We have extensive experience of how to create the best risk assessment and to ensure that your site is compliant with ATEX and local legislation. Thank you very much, everyone.